Today we're going to be looking at finding the area under the curve of the graph, same as what we did with the left and right rectangles. So it's going to be the exact same equation, which is f of x equals 16 minus x squared. And the same deal as before, we're going to be looking over the interval from 1 to 4. The difference here now is we're going to be using an infinite number of rectangles, which means we're going to have to use a limit process here. Okay, so we're going to go through quick review for those who may need it of infinite limits as something goes to infinity. Let's take, for example, n cubed plus 3n squared over 2n. Notice the highest degree in the numerator is a 3. The highest degree in the denominator is a 1. So that limit goes to infinity. Remember our application of this when curve sketching, there would be no horizontal asymptote. In fact, there wouldn't be a slant asymptote either because the degree in the numerator is 2 more than the degree in the denominator. Another example, limit as n goes to infinity of 2n cubed plus 4n squared over 5n cubed plus 3. The degree in the numerator, notice, is cubic, as is the denominator. In this case, we look at the ratio of the lead coefficients, which is 2 over 5. And our last scenario, here is the degree in the numerator will be less than the degree in the denominator. Let's take this example. So we have a second degree quadratic, a third degree a cubic. In this case, our horizontal asymptote, our limit would be 0. All right, so a quick recap there for you on our limits as n approaches infinity. So we're finding the area under the curve using an infinite number of rectangles, starting at 1 and heading to 4. Okay, so infinite number of rectangles starting at 1 and going to 4. So when we're looking at this, we still have a width from 1 to 4 of 3. The difference now is I'm using an unknown number of rectangles. I'm using n rectangles. So that's the width of every rectangle. The height is the exact same process as before, and you have options here. You can say your height is a function of 1 plus a numerous amounts of width, or you can say it is f of 4 minus numerous amounts of widths. Okay? So it doesn't matter if you start in the beginning and add rectangle width, or if you start in the end and subtract rectangle widths. It makes no difference at all. Okay, the difference it does make is how you apply it into the function. If you're going to do 4 minus 3 over ni squared, or 1 plus 3 over ni squared. I know what I'm going to do. All right, so let's set it up now. The limit as n goes to infinity of 3 over n, right, width, base, in other words, times height. And I am going to use 4 minus 3 over n I, f of that, of course. I is going from 1 to n, because n is heading to infinity. So look at what I have here. I have the base, the width, whatever you want to call it, times all the individual heights, right? If I plug a 1 in, I get 4 minus 3 over n, 4 minus 1 width. If I plug a 2 in, I get 4 minus 2 widths. Right, so that puts me at the second rectangle, third rectangle, fourth rectangle, so on and so forth, till I get to an infinite number of rectangles. Very abstract thought. So now we just have to go through, and we've done the application piece. Now we need to do the algebraic piece. We've made sense of the diagram, hopefully. I going from 1 to n. That's a bad I there. There we go. And now I'm going to actually square this, and you'll see in a second why I chose 4 minus instead of the 1 plus. So I have 16 minus my x value squared. So 4 minus 3 over n times I, quantity squared. Normally, if I'm doing this on my paper, I'm squaring this before actually writing it. I'm not even going to bother writing it. I'm just going to square it. That's your call, though. Okay, I'm going to jump forward and back here to make sure our stuff comes back, all those negatives and things that disappeared. Bless you, Abby. Sorry, my daughter sneezed. We have the limit here as n goes to infinity. She has a big smile on her face right now. The sum, I going from 1 to n of 16 minus, now I want to square this, 4 squared is 16. Remember, our middle term is going to be two groups of 4 times 3 over ni. So that's going to be minus 12 over ni doubled. So that's 24 over n times I, and then plus 9 over n squared I squared. And now I think you clearly see why I chose the 4 instead of the 1, because boom and boom. That's good stuff there. Alright, so the limit as n approaches infinity, here's the width of my rectangle, and here are all of my heights. This part's a little redundant here. I wouldn't normally write this out if I was putting this on my paper, but I'm showing the steps. I'm going to distribute through, so 24 over n I minus 9 over n squared I squared. And now I'm going to apply my rules of sigma, which is the step I normally would have jumped to right away. Alright, so I have 3 over n, my width, times all my heights, 24 over n. Now the sum, as I goes from 1 to n of I, is n times n plus 1 over 2. Minus 9 over n squared, right? That's my constant. The sum, as I goes from 1 to n of I squared, is n times n plus 1 times 2n plus 1 all over 6. And this is where that quick little limits review comes in handy. So I look at the limit as n goes to infinity of the first one. And remember, 3 over n is really being distributed to both of these. So that adds a degree to my denominator. Degree here is n times n, which is n squared, and n times n, which is also n squared. My lead coefficient, if I would actually multiply all of this through, right, I'd get 1n squared times 24 would be 24n squared times 3. So my lead coefficient is 3 times 24. And the denominator, I have a 2n squared minus, degree in the numerator is n times 2n. That's a 2n cubed, so 3. And n times n squared, also 3. So I'd look at my coefficients. Again, if I would multiply this all through, I'd have n times 2n, which is 2n cubed, times 9 is 18n cubed times 3. Okay, so all the coefficients are part of my numerator, and likewise in the denominator, the 6 is there. Okay, so at this point, excuse me, I just evaluate. 24 over 2 is a 12, so that gives me 36. And 3 and 2 is 6 over 6. They cross out, minus 9. I am looking at 27 as the area under the curve, and that is the exact area of the curve. Shortly, we'll be heading towards what is called the fundamental theorem of calculus, in which case we'll be able to do this problem in a matter of 30 seconds. Hopefully you'll appreciate that process after seeing somewhat of a tedious nature of this process here, but I hope you find it a gratifying process as you complete it. That's all I got for you today. Have a good one.